Before we begin, I want to say that the models we will be discussing in this lesson are constantly debated within the policy and scientific arenas. What model to use, what its proper use is, and what conclusions to draw from them are constantly being reassessed and debated. It is important to criticize the way you and our community think, and you will need to question yourself and each other. As a side note, I am included in this. So now let's start to look at predictions and models in this brief overview. First, I want to cover a few definitions. A model is a description of a system or some part of a system. A system is a collection of objects. An object is a unit upon which measurements or observations can be made. A description is a signal that can be decoded or interpreted by humans. These definitions imply that virtually everything is a system and that models are used and defined in almost every part of human life. Models help us describe a system, but describing a system can be variable. We can look at these three portraits as an example. If we look at the portrait on the left, it looks very similar to reality, but as we move to the right, the pictures become more abstract. So the way that each artist is modeling their subject is variable, and that is much like the systems that we use in science. In science, we often use models to help us understand a certain process. In this outline, you can see the basic steps of a model. You input certain parameters, the model predicts the system process, and the output is given. We can also dissect these different parts for different types of knowledge. If you are modeling flame length, you can synthesize or solve for the equation that will predict a flame length if you have the input, in this case surface fuels, and an observed flame length. This you do to understand the system itself. If instead you want to predict a flame length on a site, you can employ known equations or system to your measured inputs, or surface fuels in this case. You use a model in this way to predict some set of outputs. Finally, we can work backwards given a known flame length equation and observed flame lengths to determine the fuel loading that existed on a site before the fire. And a model can be used in this way to control future sites or areas so we experience certain outcomes, or in this case, fire behavior in the future. In logic theory, there are three kinds of reasoning: abduction, deduction, and induction. So what do these mean? Deduction is when we determine the conclusion based on a rule and its precondition. Induction is when we determine the rule after numerous examples of the conclusion were viewed given a precondition. Abduction is when we determine the precondition using a conclusion and a rule. In other words, we assume precondition could explain the conclusion. To illustrate these concepts, I will use a few examples from Wikipedia. In the deductive type of reasoning, we make the following statement: when it rains, the grass gets wet. This is our rule and its precondition. It rains, thus the grass is wet. This is our conclusion based on the above rule and precondition. This type of reasoning is commonly associated with mathematics. A scientist or statistician, however, often uses inductive reasoning. In this case, the conclusion is measured from the precondition. Every time it rains, the grass is wet, and a rule is developed. When it rains, the grass gets wet. So abduction would combine the rule, when it rains, the grass gets wet, with the conclusion of the grass is wet, to determine the precondition of it must have rained. This type of logic can be viewed in any episode of Law and Order or any other deductive show on TV. These concepts are important to think about because they will help us identify types of models as well as provide insight into what assumptions might have been made. For example, in both abductive and deductive logic, we must assume the rule to be correct. In the case of deduction, a false rule will lead to a false result. In the case of abduction, we could lead to a false precondition if the rule is false. In inductive reasoning, the rule is believed to support the conclusion, but is not ensured. There are multiple types of models that are used throughout social and biological sciences, including conceptual or verbal models, diagrammatic, physical, informal, or mathematical models. For this class, we will only cover mathematical models, as those are the ones we tend to use most in the field. There are three types of mathematical models: empirical, semi-empirical, and physical models. A model is broken into one of these three classifications depending on what type of equations are in the model and the structure of the mathematical incorporations. For example, here are three different equations that are used to predict rate of spread. Empirical models tend to be the simplest. Semi-empirical tend to have a few more parameters and inputs, while physical models tend to be quite complex. Empirical or statistical models are composed of statistical relationships which are developed from experimental data or historical studies. These types of models can only be applied in areas with identical conditions as those in which the relationship was formed, or where verification studies have been conducted. Semi-empirical models were developed from a combination of statistical relationships and theoretical expressions. An example of a semi-empirical model is the Rothermel surface fire spread model, which is based on the laws of heat transfer, but was completed with experimental data. These types of models can be applied in situations which have similar conditions to the experiment that was used to create them, but they are more limited than purely physical models. There are also some issues with the validation of semi-empirical models, but not as many as physical models. Theoretical or physical models are based on the equations which govern fluid mechanics, combustion, and heat transfer. These types of models are appealing because they can be applied to a wide variety of situations. However, they often are extremely difficult to verify, so their accuracy is largely unknown. Theoretical or physical models are similar to what many people call mechanistic models or first principle models. Before we move forward and talk specifically about how fire models are classified, I would like to bring up a few more terms that might help you in identifying and classifying models. First, you should know the difference between a dynamic and static model. A dynamic model is one in which changes over time are explicitly shown, whereas a static model is one in which the changes in the model over time are not explicitly shown. A continuous model is one in which time and/or space can take on any value. That is, we can model any point in time. A discrete model is one that either time or space must take on an integer. That is, time can be 1 year or 2 years, but not 1.3 years. Lastly, you should know the difference between stochastic models and deterministic models. Stochastic models are ones which include a random variable, whereas a deterministic model treats all variables as a constant. In other words, in a deterministic model, if we put in the same values over and over, we always get the same answer. Think of the Rothermel's fire spread model. Whereas in a stochastic model, we can get multiple answers with the same value. Here I'd like to outline some of the constraints on models. When developing models, we have three constraints we must consider. Realism, the degree to which the model represents the real world. The equations are correct, not just the output. Precision is the accuracy of the model predictions. And generality, the number of systems and situations to which the model correctly applies. Each of these will have a trade-off with the other two. To help make this a little more clear, if you are concerned about predicting what will happen in the future, you need very little generality because we are usually concerned about a particular place in space, but we need great precision. In this, the reality is mixed because as long as we have great precision, we don't necessarily need to know the equation that went into it. For really good understanding, it implies that we need good generality, meaning that if we want to know what is going on across the landscape, we need to have the parameters set across a large landscape. But in doing this, we tend to have less reality and the precision is less strong. Conversely, if we want more control, we want greater reality because we want to know the parameters that are going into the model, but we are less concerned with the precision and generality of these equations. Based on our current scientific thought, the principal task of science is to generate hypotheses, theories, or laws, and compare them with experiences and observations. The problem with this, as many have realized, is that it works reliably only if we are dealing with closed systems. Remember that in this thought pattern, our conclusion can only be correct if our rule is a complete description of the system, or if the system is a closed system. In reality, no system is completely closed, but systems do have different levels of openness. Therefore, in natural systems, there are always external contingencies that may not be fully specified or even known. So when we build a model, we must make assumptions about these other factors, such as completely frictionless surfaces, perfect predators, or homogeneous fuels across a stand. Another way to think about this concept is to compare a natural system to an artificial system. As I just mentioned, all models are open. Their conclusions are not true by the virtue of the definition of the terms, and they only represent a system. With this in mind, it is easy to see how no model completely encompasses any natural system, and by definition, a model is a simplification. We simplify the natural systems so that we can make them tractable. This leads us to the question of how models might be considered open. First, a model can be considered open with respect to its conceptualization. For example, when we create a model, we abstract from the natural world certain elements that we believe to be important to the problem and omit all other factors. It is these other factors that are omitted which make the model open. There are many models in science that have omitted certain factors, which latter were found to be important. In other cases, we might want to include a factor but cannot due to other reasons. Money and time are big ones. Models can also be open based on the adequacy of the governing equations. There is a great deal of philosophy that goes into this argument, but the bottom line is that we really have no way of knowing how well our laws or governing equations actually represent the system. They are simply our best approximations of what is going on in the system. Finally, models may be open with respect to the inputs. This idea is a bit tricky. On one hand, we know what the variables are, but on the other, we have to make choices about how to best represent those variables. For example, we know that canopy bulk density is important in predicting crown fire spread, but how do we best represent this value? Do we use a mean, the highest value, the lowest value? All models are open for one or more of these reasons. The more we do not know about a system, the more open it is. However, be aware that understanding a model is open is not saying it is bad, it is just acknowledging its limitations. The whole idea or concept of decision-making is to look into the future and predict what is going to occur, typically to either prevent it from happening or to be prepared for what will happen. In essence, making a decision is a forward-looking process. We look into the future, formulate alternative actions, and select among them based on our expectations of how things will turn out. It is with this idea that we can begin to see why the predictive capacity of science holds great appeal for policymakers and decision makers. This type of logic has led some to suggest that predictions can ultimately replace or become a substitute for political or moral decisions involved in policymaking. Predictions serve two goals in our society. They test scientific understanding, and they serve as a potential guide for decision making. It is the second goal that we are most concerned with as land managers. The question we need to consider is if the use of a prediction, which proves a scientific theory, is adequate for dictating public policy. Or in other words, just because a prediction is scientifically valid, does that mean it is equally valid for management and decision making? Sarowitz et al. 2000 have identified 6 major concerns that must be considered in evaluating the capacity of predictive research to contribute to positive policy outcomes. The first concern with using a prediction in policy is that the phenomena or process we are trying to predict may not be easily predicted across useful geographic or time scales. As an example of this, we can think about the inability of science to predict earthquakes. As a result, the best scientists can do is attempt to predict the occurrence of an earthquake aftershocks to provide a warning to distant areas after the one occurs. The second concern which must be considered is that accurate predictions of phenomena may not be necessary to respond effectively to political or socioeconomic problems. This concern could be tied back into the earthquake example we were just discussing, or you could think of floods or hurricanes as well. In all cases, building codes and engineering methods can be applied to reduce the damage without needing an accurate prediction of when and where the event will occur. The third concern is the idea that necessary or feasible political action may be deferred in anticipation of predictive information, which in many cases may or may not be coming soon. To help illustrate this concept, I would like to talk about long-term nuclear waste disposal, where actions may be and often are delayed due to an anticipation of nuclear waste. Beginning in the 1940s, the production of plutonium and the eventual production of nuclear reactors began to create large amounts of high-level radioactive waste, and as early as 1957, a committee had advocated that the best way to store the waste was in a large, deeply mined geologic repository. The process of selecting a site was underway in 1986, and the list was down to 3 sites. Some 30 years after the original report, a site was still not selected due to a lack of low uncertainty scientific predictions, though much effort was put into these predictions. By 1987, the Yucca Mountain site was selected. Since that time, predictions have been made and remade with newer science, and the open date is now scheduled as March 31st, 2017. The decisions depended on an accurate prediction of percolation flux rate, which in about 5 years had changed by a factor of 40. The inability for us to predict the flux rates will ultimately mean 70 years will have passed where policymakers did not make any contributions to the issue of long-term storage of nuclear waste, making the whole thing a bit inefficient. The next concern to consider is that predictive information might be subject to misuse and manipulation. As an example of this concern, Moran 2000 cites the EIS report filed by the BLM for the Aguirre mine as a case where the model was used as a tool, not as a tool, but instead as a way to provide certainty to the predictions and to advance the BLM's predetermined agenda. The last 2 concerns that they identified are that the criteria for scientific success and prediction may be different from criteria for policy success, and that an emphasis on predictive sciences moves both financial and intellectual resources away from other types of scientific activities, such as monitoring and assessment. The last concern is related to the idea that we will wait for a prediction instead of monitoring and assessing the problem. The former concern I have listed here can be exemplified by the appraisal for oil and gas over the last half a century. Now let's recap and take a look at how this information can help us in moving forward. This lecture sets the foundation for us to look at fuels and fire models. As you look at specific models, think of their limitations and how you use them to make decisions. Including this lecture, there will be 3 lectures for this lesson. Make sure to look at all of them. See the syllabus for when the first part of the field project is due, and remember the assignment for this lesson is due at the end of the month.